My name is Chaz Boyd. I'm a PM architect in the Windows Graphics Platform team at Microsoft Corporation. And today we're going to talk about the Direct Compute API. We'll start off with some comparisons between a CPU and a GPU that may help people understand the GPU better by thinking of it using some more CPU-like terminology. Then we'll cover a little bit of the applications that GPUs are particularly good at, and how the Direct Compute API helps you target those applications, a little bit of the basic usage of that API. So today we have a fairly common number of CPUs out there that are fairly well understood by programmers. Many of them have about 4 cores today, 2 to 4 cores. Each of those cores can complete about 4 floating point SIMD operations per clock. They run at around 3 gigahertz, and this gives you effectively 50 to 100 gigaflops of performance for single precision math. They're typically two-way hyper-threaded and cost about $200, and 200 watts are consumed by those cores. A GPU is actually fairly similar in terms of price and power consumption, but it's architected quite differently. There are typically 32 cores on the CPU die. That can vary depending on the price point of the processor, as much as typically smaller numbers than that for the lower price processors. However, each of those cores can retire 32-bit single precision floating point numbers at a rate of 32 bits per clock. The typical clock rate, though, is about a third of a CPU performance today. But if you multiply those numbers together, you end up with about a teraflop of performance, roughly, from each of those cores. And another way to think of it is that each of those cores is also effectively, it's a strained analogy, but they're effectively 32x hyper-threaded as well, so that the total number of threads that needs to be resident on the machine also is a fairly large number. So the key to this is, how do I come up with an algorithm that has maybe as many as 1,000 threads that need to be executed at once? So the other thing to remember is that these processor types evolved to solve 2 different types of problems. The CPU is designed to handle a large number of relatively random access operations, so its memory subsystem is designed for high-speed access to a large number of different locations. However, the GPU is designed to read a large amount of data from roughly a single location or sequential locations in memory, more of a streaming operation. And so in that sense, its latency to go to new addresses is higher than the CPU, but its throughput in terms of peak bandwidth is substantially higher. That's because each GPU effectively implements its own dedicated memory subsystem that is optimized for that type of I/O pattern. And if you're doing operations that benefit from that style of I/O, you can effectively get a net 10 approximately order of magnitude improvement in performance per watt for that type of algorithm by using a GPU. Now, most PCs that are out there today are already effectively asymmetric multiprocessor systems where there's a CPU and a GPU in the box. The CPU and its memory subsystem are as we just described, the GPU and its memory subsystem typically also operate at 10 times faster than the CPU's frontside bus, but the connection between the two is in many cases slower than even the frontside bus. So the effort to copy data from the CPU to the GPU has to be considered when you're evaluating the net advantage of the performance on the GPU side. These numbers are very approximate. They're just rough orders of magnitude. It depends a lot on the price point of the system and how well optimized it is. So now we say we have a GPU which has 1,000 simultaneous ALUs, and the question again is, where are we going to get the processing tasks to feed that many cores simultaneously? And the answer is data elements, because only data elements come in that sort of a number. And typically all the data elements that you'll have, say, in an image like pixels, will all need to have a very similar operation done to them, which means that a SIMD architecture where there is a single instruction counter for a fairly large number of threads leads to a lot of efficiency in the performance. So to get this type of algorithm on your GPU, you need to look in the application areas that already deal with large numbers of data parallel problems. So image processing, where photo analysis and photo processing are prominent cases. Video processing, you can do things like transcode, digital video effects, and also analysis on the GPU. Audio also deals with large numbers of relatively small and simple sample data structures. Linear algebra is a new area that the GPU is starting to become utilized a lot for as people find data parallel algorithms for more and more of the problems in that space. And this has led to more applications like simulation and modeling where these techniques are applied in the technical, financial, and academic industries. As an example of a media processing scenario, this is a demo of video stabilization performed using DirectCompute. So here we see, on the left side of the frame, original raw footage taken effectively with a shaky cam. However, by using DirectCompute, we've been able to process that data to remove the oscillations introduced by the person walking down the street and create a stabilized image as a result. One important point to note on these technologies is that in many cases, applications today are written using algorithms that are not data parallel. However, in some cases, data parallel algorithms for some of these applications already exist and will need to be adopted in order to get efficient operation on the GPU. For example, in sorting, the quicksort algorithm was not particularly efficient on the GPU. However, when it's replaced with a bitonic algorithm, the same result can be achieved with far more efficiency on the GPU. Another example of the performance difference between CPU and GPU is the n-body simulation calculation, which is a fundamental component of used in astronomy but also in molecular modeling. And here we see a case where we've got two configurations of relatively common machines where an SSE optimized implementation of this algorithm delivers about 13 gigaflops, and the GPU version is about a half a teraflop on the first configuration. So we see pretty substantial differences in the performance between those two configurations, the two processors on the machine. And that holds true for another configuration. I actually included these configurations because I have them, and so I know them pretty well, and I can vouch for these numbers. Now, at this point, I'd like to demonstrate another example of an image processing algorithm implemented on the compute shader that performs image cleanup. In this demo, we're using compute shader operations to perform removal of periodic noise from an image using the FFT algorithm. In the screen, you can see on the upper left there's an image of the world that has a periodic noise pattern imposed on it. If we take the FFT of that image, which you can see on the lower left of the screen underneath it, this results in clear points that correspond to the frequencies of the noise pattern that's present. In this interactive application, the user can take a pen tool and actually erase the spikes in the frequency corresponding to the frequencies of that periodic noise. This has the effect of effectively removing that noise pattern from the data, as you can see by the cleaned up image in the upper right. The lower right of the image is the phase of the FFT. Here we can see some early results that were obtained in terms of benchmarks during the development of this FFT algorithm that compare the performance at different data set sizes. The axis along the bottom is the 2 to the n number for the size of the data set that's being processed, and then the number on the left is the number of gigaflops achieved as according to the standard FFT metric. So now we're going to discuss a little more specifically the Direct Compute API, which is Microsoft's solution for targeting this, the GPU computing scenarios. First, we'll see where it fits relative to the other components in this field, some unique characteristics that it has, and what the some basic usage of the API itself. So the Direct Compute API is a very low-level kernel-based language that is built directly on top of the processor as part of the DirectX suite of technologies. Typically, it would have higher-level components layered on top, either in the form of application libraries or domain-specific languages, and then applications would be built on top of that. Although the applications can be also constructed directly on top of Direct Compute. So initially, the GPU was recognized as viable as a floating point accelerator, which there was a market for those already in the technical space that included academic research and numerical methods and these scientific and technical spaces. When Direct Compute was introduced, we recognized the importance of adding additional scenarios to these technical market scenarios that were focused on consumer and large quantity client applications. So in order to meet those types of requirements, some additional capabilities were provided. For example, it's very difficult to restrict the number of vendors that are going to produce the hardware that's in that your application is going to run on. In the technical space, you could buy an entire lab and stock it with the same brand of hardware, but when you're producing client applications, you really don't know what the hardware is. So in that sense, Direct Compute needs to run on a large number of different versions and vendors of silicon. It also needs to have tight integration with rendering, because in many cases the client scenarios are designed for interactive real-time use, and in that sense Direct Compute has been tightly coupled with Direct3D to enable that to happen. Then there are also a large number of media data types that are important for consumer scenarios that the hardware has the capability of providing high-speed format conversion to and from. And this was exposed through Direct Compute as a way to target those scenarios more efficiently. So as a result, these consumer scenarios include not just the standard technical simulation and modeling scenarios and the media scenarios, but also the game technologies like physics and AI, occlusion calculations, advanced lighting calculations that are used in rendering games as well. So the overall usage pattern for Direct Compute is as follows. You will initialize the API and then submit code in the HLSL language, which is compiled using the DirectX HLSL compiler. That code is then loaded over to the GPU, and then some data that you're going to process with that code is also transferred to the GPU ideally, and then a view is created into that data buffer so that access can be efficient. That view is bound to the device effectively, making it the current view. The execution of the code is initiated, which reads in the data from the buffer, and then the data is emitted from the GPU, typically back into video memory, and then that data buffer is copied back to the system when you're done. So there's some I'm providing examples of the typical syntax that's used for these steps. To initialize the API, we have the DirectX 11 create device call, which is not particularly different between when it's used for direct compute and direct 3D rendering. This is an example just to give people an upfront view of what it looks like. That HLSL is our effort at this point to try to make programming the GPU as similar as possible to C or C++. So the syntax that you'll deal with when you're working with HLSL should be familiar. In this case, it's a very simple algorithm that's just taking the contents of two buffers and writing it into a third buffer. Technically, if you look at, say, the number of installations out there, HLSL is probably already the most widely used data parallel programming language, because it's been used in mass market games for many years. The fundamental operations are very similar to C. However, there are some important differences. There is no support for pointers in HLSL, which makes some implementations substantially easier. Built-in variables and types are included for things like float3 and float4 and some matrix data types, and then some more vector-oriented intrinsics are also included. So the compilation process is actually a two-stage approach. The first stage is to compile the HLSL code using either an entry point in our library or via an offline command line tool called FXC. This generates an intermediate language which the definition of that is owned by Microsoft. The optimization effort spent into this stage is very significant. At that point, now you have what amounts to something analogous to an OBJ in terms of a compiled shader. And then that is passed to the hardware at the time it's needed to be executed for a final JIT or a translation step that converts it to the actual binary instruction set for that chip. This is a relatively quick step, as done at runtime, and uses the create shader API call to perform that. So this is an example of a call to compile. We have a utility function in D3DX that takes in a source file name as an individual file that you can load directly as a convenience function. Then once the shader has been compiled, you get back a pointer to it that you can then at runtime create the actual shader handle from, and that is then used to transfer to the GPU for it to translate to its actual instruction set. And then before you can actually execute that shader, you need to get a pointer back. You need to set that pointer to the shader pipeline as the current shader to be executed. And then, as I mentioned initially, there is a create buffer step where you define a range of memory that is to be considered the input for this processing step via the create buffer API. And then you'll build a view onto that. So this diagram clarifies the relationship between buffers and views. Originally in DirectX, we really only had the concept of the resource object itself, but in recent versions, we've introduced the concept of a resource view, which enables quite a few additional features to be implemented efficiently. So the DirectX resource itself really just defines a range of memory, and typically in video memory, but also potentially in system memory, that enables improvements in security and reliability because it guarantees that any accesses to that object will be isolated to that range. So any attempt to read outside of that range returns a 0, and any attempts to write outside that object memory range are ignored by the implementation. And then the other advantage to using these is these are basically the fundamental currency that DirectX APIs use to communicate with each other. So of the resource types, there are really two broad categories. The first is a buffer, which is really a sequential set of data records. You can define the structure to be anywhere from just an arbitrary D word to a fairly long and complicated structure with, in some cases, hardware format conversion for some of the elements in that structure. The texture version of the resource is one that's specifically optimized for image processing, especially sampling, and that the buffer itself defines the layout as to whether it's a 1D, 2D, or 3D buffer. The buffer types support an unstructured variant, which is potentially useful for some applications where the type of the format is going to be varied substantially. But both of these buffer types can be used to support both random access and streaming sequential I/O. On the texture buffer type, the actual layout of the data in memory is can be subclassed into a more specific data structure that ranges from just a 2D array, or a 3D volumetric data layout, or the surfaces of a cube, which is often interesting for certain imaging algorithms, like skyboxes in games. Okay, and then once the buffer has been defined, we need to define what the view into that buffer looks like. In this case, we're going to be creating a buffer that takes advantage of the compute shader's ability to do random access I/O, which means that we'll be creating an unordered access view into that buffer. The view itself is really this additional mechanism to provide information about the buffer and the operation that's going to be done to it in terms of reads and writes, that provides more information for the API, but the possibility exists to create multiple views into the same buffer, which creates effectively a polymorphic approach to accessing that same data. For example, creating two different views onto the same resource using different pixel formats means that you can effectively get pixel format conversion between those pixel formats. The unordered access view is the one that's most interesting from the compute shader perspective, since it allows the random access I/O operations that the compute shader supports. This is a relatively new thing for DirectX, because up until DX11, the DirectX APIs didn't support I/O to any destination that wasn't known at the time the shader was launched. Okay, so that's just a rough overview of the way the basic initialization, the way direct compute fundamentally works. I've included in this presentation some terminology that will help developers understand the discussions in the following slide and in the other lectures presented as part of this series. Okay, in summary, the key point is that GPUs can really deliver typically an order of magnitude performance boost, at least for data parallel algorithms, over a CPU for a given amount of dollars and watts. Data parallel algorithms such as media processing are a key example. The Direct Compute API is Microsoft's solution for this type of general purpose GPU programming, as it has been extended to support client scenarios. It's built on the DirectX technology foundation, which facilitates real-time interactive use of these solutions, and also integration with the other DirectX components that already exist. Thanks for listening. I hope this has been helpful. Please check out some of the other presentations that will provide more detail as part of this lecture series.